What do you think? Should we continue? So we were looking at this illustration on the top board of this second moment where you fix something on GL2 and then you twist by something on GL1 that you vary over some big family. So this was an example that we already saw in Philippe's lectures, and so we traced that example through the application of the summation formula for the chi's, which is very simple. It's just orthogonality of characters mod q, to arrive at an expression, this last thing on this top board, where you take a sum of lambdas over a dyadic interval of size q, but with the additional constraint that the summands are congruent to each other mod q. And then you want to understand the asymptotics of that. So that expression, so we should have seen this in Philippe's lecture, we can break up as a sum coming from the contribution where m is actually equal to n. So let's just say we have a sum over n of size q, now of lambda squared, plus some contribution from when m is not equal to n. Okay, and so experience suggests, and okay, we know now that this actually does give a structured main terms. This is something, especially given that f is fixed, we can evaluate using the Rencontres method, so we know kind of exactly how big this thing here is. So this gives a main term of size roughly 1, and so the whole difficulty was to show that this second part here gives a lesser contribution. So, so I forget the precise notation he used, but I imagine in Philippe's talk, what came up was that you can introduce an additional variable, maybe h, given by, let's say, m minus n, and you're left then with a sum over h not equal to 0, but essentially bounded in magnitude by a constant. So it's not going to change too much. Thank you. Yes. Good. Yep. Okay. Yeah, I think that's it.
Maybe we just came back from the break, and it starts with an equal sign. I'm a bit lost.
Yeah. Okay. The equal sign is from the right side of that top board right there, because I was slow when I was raising the blackboards and I forgot to put an asterisk or something to mark it, yeah. But yeah, good question, right? Yeah, unfortunately that middle board is kind of in the middle of everything, huh? Okay, yeah. All right, well. All right, yeah, any other questions about where we are, what we're doing, why we're here, that kind of thing? Shallow questions of that nature? All right, cool. Well, if not, so then continuing, so you have basically a bounded number of h you need to consider, and you have a sum over n in an interval of size q, dyadic, and you're left with lambda of n plus qh, lambda of n bar. So this is exactly, I mean, you kind of you might as well consider the case when h is 1, in which case you need to understand how big this sum is, where, okay, you have lambda of n, but then you have lambda of n shifted by something like q, and get cancellation. And I guess in Philippe's lecture, so Philippe, I guess you did this using the delta method, so where you detect the condition that m here equal n plus qh using some family of additive characters defined modulo many moduli. And then you do what? You apply Voronoi in both variables. Did you explain the details of that? Can you remind me?
I don't know. It depends on what the audience consider.
Okay. Okay.
Depends on the audience whether to take or not.
Okay, great. Okay. Any comments from the audience? Okay, so I'll present one way to think about this, this circle of questions, and it'll have a clear relationship to what Philippe described, but it'll have a slightly different perspective, and we'll be able to kind of tweak the presentation in a couple ways. So kind of the starting point for our presentation will be just recalling what the Fourier expansion of a modular form looks like. So what was the notation we used? So lambda is the coefficient of, I guess, f, right? So a modular form usually starts life as a function on the upper half plane, given by a Fourier expansion, something like a sum over n of maybe lambda n, maybe divided by the square root of n. And so this is, of course, a Fourier expansion, so we have a term e to the 2 pi I n x. And then there's some function of y that shows up in here that, so in classical presentations, so if, for example, f is a holomorphic modular form of weight k, then this is kind of the other part of the complex exponential of nz, but typically you normalize things by an additional factor involving y to the k, and when you work out that normalization, what this Whittaker function works out to be is so some power of y times an exponential, like so. So the other main case is when it's a Moss form, say of parameter it, then this is a k-Bessel function like so. Okay, maybe that's the case of an even Moss form. For an odd Moss form, you got to reverse the sign when y is negative. So this is if f is a Moss form of eigenvalue a quarter plus t squared. Okay, so the point I just like to observe is that from this, I mean, you typically view this as a formula for evaluating f, right? You know, it says f equals something where the something involves lambda and w. So if you wanted to, say, compute f, you could write a computer program that, you know, takes in all the lambdas, takes in a description of the w, and then evaluates this series to high accuracy by truncating it at some point. But you can also view this formula as a tool for studying sums involving lambda. Right? So rather than reading it left to right, you can read it right to left and say, hey, maybe by chance in nature I encountered the sum over n exactly like this. How can I understand this? Well, okay, I already have a modular form over here that is exactly equal to the thing I'm interested in. And this modular form, it's a modular form, right? So modular forms, you know, they have this like nice fundamental domain where you can kind of read off all their values from. So maybe the point where I'm trying to evaluate it lives in that fundamental domain. All right, good, I get some value of it. Maybe it's very high up in the fundamental domain. So in that case, we know that the modular form decays rapidly, so we know that the sum we're looking at is very small. And finally, maybe we're looking at something where we're evaluating the form outside the fundamental domain. Then, of course, we can play around with the modularity and kind of reflect it until it eventually lands in the fundamental domain, and then we have a more useful sum that might kind of give a more computable formula for what we're interested in. And I mean, this shows up all the time. So for example, even if you take x to be 0 here and just let y be a positive real, that maybe you let shrink to 0 along this vertical geodesic, then you know, this formula becomes quite unwieldy when you let y be very small, because the effect of this function w is to truncate n to a range roughly comparable to 1 over y. So if y is getting small, that range is getting quite large, and you need more and more terms in this series to asymptotically evaluate it. But of course, you can just invert y, replace y with 1 over y to get a point that lies in the fundamental domain. And then you're in good shape to evaluate it. So these ideas, they kind of show up very practically if you're interested in, say, numerical evaluation. Can also be very useful as starting points for looking at things like what we have on this right-hand board here, where, okay, maybe we don't exactly see from the very beginning a sum exactly like what we have right here on this right-hand side. But you can imagine trying to massage this right-hand side maybe after squaring until it looks like this stuff we have over here. So let's actually do that. So let's go back to that top expression on the board up there. So I'll write it again so we don't have this, room height long equality again. So let's imagine that we were actually interested in a sum over m and n as above, with m congruent to n modulo q. And then I'll continue to write down the thing we had above, so lambda of m, lambda of n bar. But okay, let's remember m and n were of size roughly q, right? So in fact, we initially had square root of m and n appearing there. That was kind of the more natural thing from the very beginning, okay? So I haven't written down the condition that m and n be of size comparable to q, but let's imagine that we impose that condition by evaluating m and n at this function w, or under this function w, like so. So I hope you'll agree that the expression I've written here, up to the precise shape of w, is exactly the expression we started with on the top board on the right side. Okay? Does anyone disagree? I'll give you a point if you disagree and you're correct. Yeah. Yeah, exactly. So I mean, just for now, I'm saying, okay, maybe this W looks something like that, whereas the actual W that we cared about at the beginning looks like that. And then the point that I'm going to kind of return to after illustrating this in a basic example is that you can have your cake and eat it too by choosing your vector more flexibly. But yeah, for now, let's just imagine that we're kind of doing it with a different cutoff than the one we're given. Yeah? No? Okay. All right, so, well, you can, of course, detect the condition that m is congruent to n mod q using multiplicative characters, as we did above, more or less. But you can also do it using additive characters, right? So claim is that this is exactly equal to 1 over q times the sum over all a mod q. So this is just my shorthand notation for a in z mod qz of the absolute value of f evaluated at, so I got to choose some numbers x and y, a plus I divided by q squared. It's m congruent to n. You're asking what does this mean, or? So there's yeah, okay, so let me say it again just to make sure it's clear. So we started with the thing on the very top there, where there is just the condition that m and n be congruent, and we don't kind of further divide the sum. And so we can skip from that top board directly down to this, up to the mild lie that we're replacing w with a slightly different cutoff. And then we have this exact identity. And what I was recalling here is what happened in Philippe's lecture, where we immediately treated the diagonal case where m is equal to n or not equal to n differently. But never do we treat separately the case that m is congruent or not congruent. That congruence condition is kind of always imposed. Does that make sense? Okay. Okay, so yeah, I'll leave this maybe as an exercise just to check, but It is a simple exercise. It's just the Parseval identity for Z mod Q. So if you expand out the formula for F that we have here, and then bring the sum over A inside, it'll exactly detect the condition that M and N be congruent mod Q. And moreover, I've chosen the imaginary part here to exactly pick up M divided by Q and N divided by Q. Okay. All right, so now we run into the problem of actually making sense of the asymptotic evaluation of this kind of expression here. And if we go back to this picture that I maybe drew a little bit too small. So these points here, maybe I give them a name. Maybe I call them, so call this point maybe Z subscript A. So what do they look like? Well, of course, Q is getting very, very large. So they'll have imaginary part 1 over Q, which will be very small. And then they'll fill up this interval here with horizontal spacing 1 over Q. They'll kind of fill up all the integral points in there. And so now when you take this range and you project it back to the fundamental domain, it'll look something kind of crazy like this. And so this collection of points, it's not the same as the collection of CM points that Philippe used in his lecture in a very similar setting, but it's closely enough related. And it's a collection of points that we again know enjoy equidistribution in the limit as Q goes to infinity. So, so we know, in fact, from that equidistribution fact that I just alluded to, that this converges as Q goes to infinity to just the integral of the squared magnitude of F over, over the appropriate quotient, so H mod SL2Z or whatever. Okay, and that is, in some sense, then the end of the story. Because, so the convergence that we have here is kind of sufficiently robust and uniform that you indeed have a structured main term, just given by the integral, and the error term is likewise robust, meaning it kind of behaves at most polynomially bad as you start deforming F. And there's a power savings as well in the rate of convergence. So this then becomes kind of the whole story. And yeah?
You may also say, just for adding that this is the Ecker bit of I minus 1 point.
Yeah, that's a good... Yeah, that's a good point to make. I mean, at that rate, maybe I should just sketch the proof of the convergence, and I think, yeah, I think that would be a good thing to throw in. But okay, yeah, are there any questions? Because now, okay, modulo the lie replacing the cutoff with the W that we've written there, and modulo this equidistribution assertion that we're using as a black box for now, this kind of completes the proof of this moment evaluation. And so then to turn this into an actual subconvex bound proof, all you'd have to do, which would require some, kind of writing down and bookkeeping, is throw in an amplifier and kind of keep track at each step in the proof how the amplification affects things and verify that it in fact blows things up only at most polynomially in the length of the amplifier. So we're done. That's kind of really that's really the whole argument kind of at a high level. It's just that one identity there after the top identity on the top board. So maybe it seemed kind of short and simple, but it, it actually kind of is. All right, so sorry, you had a question. I don't know the best reference for this equidistribution result. I'll explain it in just a second. But I mean, well, okay, I'll write down something. So this here is, you might call it like distribution of Hecke orbits or Hecke points, something like that. But I'll sketch the proof, so we'll have some. But okay, any other questions while we're erasing here? You want to replace I with B times I, where B is what? Yeah, that'll be no problem. Yeah. Okay. So, okay, why do we have that convergence? So, do I give this thing a name? I don't have any asterisks on the board lately, do I? So, so first of all, we have something called kind of like the spectral expansion, which says that for all, let's say, nice enough functions psi defined on this quotient, maybe I give this quotient a name, I'll call it x. So psi is a function from x to the complex numbers. Let's say nice enough. We can write psi in a suitable sense as, well, a linear combination of kind of the eigenfunctions on the quotient that I'll write down in a second. But, oh, so why does dagger hold? Nice. Okay. So we got a spectral expansion. So the spectral expansion says, I'll kind of write it out more or less in full once. So it says what? I mean, you have a contribution from the constant function 1, and then you have a contribution from, well, let's say for each, what letter do I want to use? Kind of want to use psi, but okay, let's say phi. Phi, and let's say a basis for the space of cusp forms. So maybe it's an orthonormal basis, so I don't have to divide every time by its norm. And then you get a copy of phi. And then down here you get an additional contribution of the Eisenstein series. So you have an integral over, let's say, T and R of okay, and of course, to make anything rigorous involving this, you need to say what conditions on psi you're imposing and what sense in which this expansion holds. So for instance, if psi is smooth and of rapid decay, this will hold pointwise and will converge rapidly. And that suffices for the arguments we're giving. And so then continuing, you'd say, okay, therefore, dagger equals, or sorry, not dagger, asterisk equals, well, by the asymptotic, by the spectral expansion for psi equal to the squared magnitude of f. So you'll get this contribution of the constant term. So maybe I'll write that out just to hopefully make it clear. So you get 1 over q. Yeah, so that's a 1 right there. So you have f squared inner product against 1 divided by 1 inner product 1 times the function 1 averaged in the above sense, but that's just, of course, 1, plus, so let's say a sum over phi, as on the right board, where now you have magnitude squared of f inner product phi, and then 1 over q, sum over a mod q, phi of a plus I divided by q, and then I'll say plus dot dot dot, which means you take the bottom term here involving the Eisenstein series and you appropriately modify this contribution taking into account that term. Now, these quantities here for fixed f, so these will be kind of like the Fourier coefficients of f, or the square of f. So they'll decay very rapidly. They'll decay faster than any power of whatever parameter you feel like attaching to phi. So you can basically treat this sum, I mean, you also know by forms of the Weil law how many phi there are with parameter up to some bound. So you can basically treat this as if you had only one phi that you were looking at a time. And the goal is just to show that this expression here is bounded by q to the negative delta for some delta. And so what actually comes out is that you get q to the var theta minus a half, where var theta is a bound towards the Ramanujan conjecture. So I'll explain this in just a second. But okay, it's a week-long course on automorphic forms. Maybe we'll touch base with the Ramanujan conjecture in other lectures. So what this comes from is, so this expression, let's aggressively call it double star. And then to answer Philippe's question, so double star is just the following. You take the Hecke operator TQ, you apply it to phi, you evaluate it at kind of the identity element, or maybe the upper half plane element I, but then you subtract off the contribution of phi of qi, which is one part of that Hecke operator, and then you divide by q. So, phi, of course, we can think of as basically fixed for the purpose of our analysis. So this number here will be uniformly bounded, so it'll contribute something of size roughly 1 over q. And then tq phi will be a multiple of phi. So phi again is basically fixed, so its size is actually bounded. But we get basically the Hecke eigenvalue at q of phi. And I guess the normalization is that when we write this typically is 1 over square root of q times the unnormalized Hecke eigenvalue. So we should divide this by a further square root of q to get the actual estimate involving the unnormalized Hecke operator. And then bounds towards the Ramanujan conjecture are just literally bounds that say that things like lambda phi of q are bounded by q to the var theta. Maybe plus an epsilon if we took q to be composite. Okay, and so that's the whole argument. And so somebody asked, what would happen if we, put a b there, and the only difference is you'd have b times I here, and so that wouldn't appreciably change things. Yeah, okay. And so the last very small point that I'm going to make is just how do we get around the lie that RW is not the given W? But before I do that, are there any questions about what we presented here or elsewhere in these past few boards? Yeah, the 1 over q is just this kind of, spurious term that comes from the fact that the Hecke orbit, should I recall the definition of the Hecke operator? It's like, it consists of q plus 1 terms when q is a prime. And so that's kind of the odd term out. Yeah. Where does what come from? Oh, you say lambda phi of q. So this is saying that TQ phi is square root of q times lambda phi of q times phi. This is the definition of lambda phi of q, and it's the same lambdas that show up in these L functions. You're asking if does this method work for GL2 times GL2? Yeah. That'll be another one of the examples that I treat. So yeah. Yeah. You bound it the same way. The only thing you need differently is, so kind of everything goes through. You again get kind of rapid decay with respect to the parameter of the Eisenstein series. This identity persists. You just need a bound for the Hecke eigenvalues of Eisenstein series. And for those, you can even take var theta to be 0. So life is even better. Does that address your question? Okay. What do I want to erase? Maybe I erase this. Okay, so yeah, again, Philippe was nice enough to set me up for this next comment because he mentioned at the very end of one of his lectures that to an F, like on the right board, defined on something like the upper half plane or maybe, you can kind of naturally lift it to a function on the group, either SL2R or maybe a bit more conveniently GL2R. So F as on that right board, we can lift to some F tilde, so it will be a function on, let's say, GL2. So maybe F is a modular form on SL2Z. So you can lift it to a function on, let's say, GL2R mod GL2Z. Maybe I'll just call that G mod gamma for now. By sending a coset with representative G to, well, you got to normalize the slash operator in the appropriate way, but basically, after dividing through by the determinant, you take F slash G evaluated at I. And if you do that, then the function you get up here, I like to use the notation underline x plus iy, let's define this to be the matrix. I should write this bigger. I'm not using this board. Let's define this to be the matrix in GL2 given like so. So then, I guess this matrix has the nice property that when you act on I by it, so let's say you take underline Z and you act on I, you just get back Z. So it's kind of the lift from upper half plane to like the Borel subgroup, upper triangular of GL2. So the setup is such that this f of x plus iy is just f tilde of x plus iy. So you get flexibility now by passing from f tilde to an automorphic representation that we'll call pi, which is roughly the span of all right translates of f tilde under elements of G. So a right translate would mean something like you take f tilde and you put the argument there and you translate it on the right by some group element G. Okay. Are there any questions so far about just the notation we've set up? So pi, I mean, it depends how you define the word span, but so I mean it in kind of like the sense of a smooth completion. So you can think of it as a space of smooth functions on G mod gamma. Yeah. Okay, and then there's there's a very useful fact, and I mean this is an elementary fact, so it would be a suitable thing for exercises and discussions here. So it's a fact called like the basic theory of the Kirillov model. So maybe Kirillov model surjectivity. So what does it say? It says for all functions, okay, I already have W meaning something over there. So let's say for all functions V, now I'll use the same letter. For all W in CC infinity of R star, there exists a unique phi in pi such that phi of underline x plus iy is equal to this right-hand side over here. So maybe I'll just say right-hand side of above, referring to that. Okay, and I should emphasize this is really kind of an elementary fact that you can sit down and prove. It just involves looking at how right translation by group elements affects expansions of this form. They have the effect of modulating this function W. We're using diagonal translates. You can move this function W around. So it's just the observation that if you're allowed to dilate and modulate a given function however you'd like, you can cook up any function you want. So I guess that addresses the existence, and for the uniqueness, you use the fact that elements of this form have dense image in G mod gamma, which is also something that's treated in elementary modular forms books in some form. Okay, and so then, yeah, the upshot is, all right, I said we were lying in this argument because we were using the W that was given here rather than the W you're given by your problem. But the upshot here is you can just use whatever W you'd like at the cost of working with a modular form that is not maybe the original one you started with. So there are many papers, including some in the references that I've mentioned that kind of use this theme in very serious ways, in illustrative ways. Philippe also mentioned a recent paper by myself and Jana and Blomer that uses this, treating this shifted convolution problem kind of itself more directly. But okay, that's all I wanted to say. So we'll kind of go back to just ignoring the details on this board for the remaining sketches, but this is how it's implemented in practice. And so I think this is all I wanted to say now about illustrating example 1 from a couple perspectives. So again, to repeat, you do what? You expand in sums. You see this diagonal condition pop out. You inevitably have to face shifted convolution sums. You can either face them directly, or you can face them kind of explicitly or implicitly through this spectral approach indicated here. And you can actually find like kind of in-betweens of these two approaches as well, where maybe you do break it up into diagonal and off-diagonal, but then you treat each piece of the off-diagonal using something like this. So that's another exercise, just like try to write down this argument in as many ways as you can using ideas between this presentation and the one Philippe presented. The other remark, kind of along the same lines that one could make, is that when you dig in further into the theory of integral representations of L functions, you see that it sometimes can be more direct to pass from the L function as given by its integral representation to expressions like this than to pass through the intermediary device of sums like the above. So you can kind of cut the sums out of the whole picture and go directly to something like this using geometric forms of the approximate functional equation. So that's also something that would be suitable for talking about in the afternoon sessions as an exercise. So there are many, many ways one can juggle this presentation. Okay, so any questions on 1 before we go on to 2? So if you remember 2, and also I guess 3 and 4, so these are a bit different than 1 because they don't involve averaging over characters or things on GL1, but instead averaging over things on, well, GL2. So it's the first case where you have to use a summation formula that's a bit more interesting than just something like orthogonality of characters. So let's remember what we're trying to do with 2. So with 2, the problem was to, again, so we're going to take an individual chi modulo q, and we're going to vary f on something like gamma naught of q. And then we're going to try to understand, so for instance, the sum over all f. So maybe, for instance, say of given fixed weight k. And so here of course q is going to infinity. That'll be our parameter. So okay, we'll have f, and I'll just write f on gamma naught of q for a sum over a basis of elements like indicated here. And maybe, so maybe we initially care about something like L of F0 times chi 1/2 for some specific F0. So this we should recall, so the conductor here is going to be comparable to q squared, provided that f is, for example, as above. And so this will be given by a sum over n of size roughly the square root of that, roughly q. And then we'll have lambda of n, chi of n over square root of n. So kind of focusing on that largest dyadic range, maybe the thing we care about bounding is something like a sum over n of size q, lambda of n, chi of n divided by square root of n squared. I guess I didn't need to write f naught, I could just write f. So maybe we're interested in this moment, again, normalized. So, okay, we expand the square as we did before, and that leads us to something like 1 over q, sum over m and n of size q, and then let's say chi of m, chi of n, and then 1 over q, sum over f, again on gamma naught of q, of, so lambda is always lambda f, yeah, I mean, you could take f to be holomorphic of given weight, or you could take whatever kind of Archimedean condition you want, but maybe keep it fixed there just to focus. Yeah. Okay, and then you need to understand this expression right here. So this is exactly the content of the Kuznetsov, or in this case, Peterson formula. Which I guess I'll write over here. So in general, it says something like, if you take 1 over, so yeah, maybe I'll just write it in place here. So do we have enough room? Okay, I don't know. Let's call this, let's give this a name. Let's call this maybe sigma subscript m and n. And so then the formula says that sigma mn, so I'll say equal up to kind of things that'll be obvious if you look at the actual formula. So there's a delta function that detects the condition that m is equal to n. And then there's a sum of Kloosterman sums weighted by Bessel functions. So you have a sum over natural numbers C that are divisible by Q of the Kloosterman sum S of MNC divided by C, and then let's say the J Bessel function with index k minus 1 of 4 pi square root of mn over C. So okay, well, I mean the Bessel function, at least for J, for K large, kind of looks initially like this, and then kind of oscillates and like has some kind of behavior near infinity. So we've chosen M and N to be of size roughly comparable to Q. And C itself, well, it's divisible by Q, so it has to be at least Q. So this argument of the Bessel function, we know, is at most roughly 1. So we're kind of only in the part of the Bessel function where it doesn't oscillate, where we're kind of close to the origin. So this is kind of the main region of interest for us. And so there, at least if we take K large enough, which we will for this discussion, we can think of this function as kind of decaying rapidly as the argument approaches 0, which means that we can roughly think of this as, well, again, this delta function plus a sum over C congruent to 0 mod Q, satisfying the further condition that this argument is comparable to 1. Because we don't need to worry about what happens near 0 for these Bessel functions, at least if K is large. So you get the condition that C is asymptotic to square root of Mn, but of course that's itself asymptotic to Q. And then you're left with S of MNC divided by C. So the argument is, so yeah, I just kind of said it out loud. So we know that M and N are of size Q, and we know that C is of size at least Q. So this argument is kind of obviously at most roughly 1. So we don't need to worry about what happens there. And then I'm just saying the Bessel function, at least if K is large, which we'll take it to be for this discussion. So let's take K large, for instance. It'll decay rapidly near 0. So we might as well pretend it vanishes near 0, and then we're literally near 1. Yeah. Okay, and so you know, when one is first working on a problem like this, you know, you might say, okay, let's focus on the contribution of like the typical. So maybe I'll use 3 approximations to say, okay, this is really quite close to, you're detecting if M is N, and then you're just left with, let's say something like S of MNQ divided by Q. Because, okay, in general, you'll have roughly finitely many terms corresponding to all the values of C that are comparable to Q and divisible by Q, but a typical one will look something like this. So provided our arguments are robust enough, and they don't use something very, very specific about the number Q rather than, say, 2Q, whatever works for this formula should work more broadly. So now let's plug that formula in to what we were left with here and just see what happens when we try to analyze it. Okay, so yeah, we started with this expression. Let's call it star again. I think star has been reset by now. So we get that star is something like, well, okay, we'll have the diagonal contribution from when m is equal to n, and then if I put my conjugate correctly, these guys would both be the same number in that case, and we have about q terms coming from that. So the diagonal contribution will be something like 1 after normalization. And then the off-diagonal term will be, well, 1 over q squared times the sum over m and n, each of size roughly q, of chi of m, chi of n bar, s of mn q. All right, what should we do next? Any suggestions? Because as we've said at this point, we've, kind of the theme of the course is like, subconvexity for automorphic L functions, right? So kind of the hard parts there in some sense, or maybe the mysterious parts are like automorphic and L function and all of that. But now we're at a problem that, can be understood kind of independently. So, okay, maybe I haven't recalled the definition of the Kloosterman sum, and that would be a good idea to do at this point. So it's a sum over units A modulo C of e to the, so this means e to the 2 pi I whatever over C times ma plus n A inverse meaning modular inverse. So this is just a sum kind of in pure analytic number theory involving Dirichlet characters and exponentials and Kloosterman sums that you can try to attack using any tool you want from there. So kind of the standard maneuver at this point is, you're looking at kind of character sums that are nearly complete, meaning, in fact they are. So they're over a range that is of size comparable to the modulus with respect to which they're defined. So you basically know that if you apply Poisson summation to something like this, you'll get dual sums that have bounded frequencies that show up. And so you should be able to kind of analyze this kind of expression very well in terms of complete exponential sums modulo q. And so I'll just say that the next step here is Poisson summation in both m and n. And what this eventually gives rise to, if you carry out the details, which I won't, but again, that's a good exercise to try if you haven't done this kind of thing before, like think that through. You get complete exponential sums that look something like, so you'll have to face something like a sum over maybe let's say A modulo Q of chi evaluated at A inverse times some fractional linear transformation applied to A. So here gamma lies in, for example, SL2Z. And these are things that one knows how to bound and determine the size of very explicitly using like Bayes' theory, the Riemann hypothesis over finite fields. So that's not a chapter I'm planning to enter into further here, but it's one that would again be interesting to think about if you want. Okay, so I mentioned I give a couple perspectives on each of these. So there are many ways you can attack this same problem, kind of, again, basically exploiting the interplay between sums of coefficients and values of automorphic forms. So you can do the same thing here, right? Because, I mean, the basic observation is that, so the sum we started with, the sum over n of size q of lambda of n, chi of n over square root of n. So I claim that if we make this a bit more explicit by writing the weight function as w n over q, then this is exactly equal to something kind of like what we encountered, I guess, in some now erased board. So it should be, hope I get this right, let's see, q to the negative half maybe, times the sum over a mod q of, oh, okay, yeah. So there'll be a chi bar of a, what did I call it, f of a plus I over q. And okay, it won't be exactly that, but it'll be like the Gauss sum of chi, what will it be? Divide by the Gauss sum of chi bar, yeah, 1 over that, let's say. And this, of course, has absolute value equal to q to the negative half. So it's of the size I indicated. So this is a simple exercise to check that if f has the Fourier expansion from a few boards ago, then you can write a sum like this in terms of the values of f, again along the same collection of points that showed up in the illustration of moment 1. Yeah. Okay, so you can continue to analyze this moment using this formula by now introducing a kernel function, so I'll call k of zw, which is basically the sum over all f. I don't know if you want to make it an average. So f on gamma naught of p in the same sense as above where you fix the weight, but I won't write that here for clarity. And then you take what? F of maybe z, yeah, maybe f of z, f of w conjugate. So the theory of the pre-trace identity or of reproducing kernels for spaces of modular forms gives you other ways to understand this, this sum. So I'll just write down here, you apply something like a pre-trace formula, or in holomorphic cases, you can use something called a reproducing kernel. So just to give you some things to search. And what this comes out to is a sum over gamma in gamma naught of p of some kernel function, maybe I'll call it phi for now, of, well, the matrix attached to, this is the way I prefer to write it, z inverted times gamma times the matrix attached to w. And then using this formula, you can very quickly open the square that you get by inserting this identity into the middle board. And you'll quickly arrive at what? So this expression that we called star on the middle board will be 1 over q times the sum over a and b, let's say, modulo q, of maybe chi bar of a times chi of b, and then a sum over gamma and gamma naught of, sorry guys, I called it p, but it's really been q. All right. So sum over gamma and gamma naught of q. And then you get phi of, so the same points that I called ZA before, underlined, and then gamma, and then let's say ZB underlined. And now, I mean, what I didn't maybe emphasize over here originally is that the fact that we're averaging over a family of forms of some given weight, maybe we take the weight to be pretty large, says that the function phi, so it's some function on the group G, right? So this is a one-dimensional depiction of the group G. And it's a function that looks kind of like this, meaning it decays rapidly away from the identity, where the speed will depend upon k, but we can take k to be big just for the sake of illustration. So this is basically an expression now that detects the condition that this product of matrices is very close to the identity. So it's something you can analyze quite explicitly. Maybe for the sake of time and coverage, I will not continue this line further, but you'll very quickly get from analyzing this expression back to complete exponential sums of this form. And so, you know, maybe depending upon your taste, well, no, I mean, I think quite arguably this is a more direct way to get to those kinds of exponential sums than passing through the intermediary of the approximate functional equation and the Kuznetsov formula, and then two applications of Poisson summation. But all the methods are kind of useful for various, there are pros and cons to all of them. But it's good, so it's good to be kind of aware of all of them and to try them all when one can. So I think that's all I wanted to say about, I wonder if this already might be a little heavy, but I thought I would try to survey moment example 4, just quickly, just to give another example of how one can, in a few minutes, sketch the main ideas of these papers that maybe are a bit longer to kind of fully elaborate, with the idea being that then you'll have something to go sit down and think about and use as a guide maybe to look at the original literature and dig in deeper. And also, I've been very light on attribution in this Blackboard presentation, but a good number of the papers that I'm implicitly referring to here you can find in this reference list that accompany the exercise list. So for an illustration of 4, so I guess the version I'll consider is, let's take f, again on gamma naught of p, and we could, for example, consider the 4th moment of the standard L function for f, but instead we'll consider, so like in this paper of Philippe that I mentioned, this kind of twisted 2nd moment. So we're here, G is on GL2, maybe G is fixed. And P, I've been usually calling Q, so maybe I'll try to continue doing that. Okay, so again, this thing has conductor, roughly now Q squared, because you're twisting by something on GL2, and the original thing is conductor Q. So the approximate functional equation will give a formula for this that looks something like a sum over n, at most roughly the square root of that, and okay, if you've seen the formulas for Rankin-Selberg convolutions, you know that they're not exactly of this shape. There's an additional zeta of 2s that appears in front that you have to take a limit with, but okay, morally you get something to leading order kind of like this. And yeah, if you now try to average, okay, you're faced with, let's say we focus on the largest dyadic range, so we're say n is asymptotic to q. Then you're faced with a sum over, let's say m and n of size q of, so lambda of n bar divided by root mn. Let's just write lambda as short for lambda g, because that's the one that'll actually persist. And then if we normalize it by averaging, we'll be left with basically the same thing we had before. So you'll have an f on gamma naught of q of lambda f of m, lambda f of n. And this is exactly this expression that we called sigma mn on the top board, right? So this was sigma nn, which we agreed on this upper right board was something like a diagonal contribution plus, and let's just say the Kloosterman sum S of mn q. So then if you plug that in, you'll get, well, the contribution of the diagonal term plus the off-diagonal contribution, which will look like what? Like a sum over m and n of size q, and maybe I pull out the leading factor of 1 over q from the square roots, and then lambda of m, maybe lambda of n bar, although it's real, S of mn q. Oh, thank you, yeah, you're right, yep. Good, so yeah, maybe let's make it 1 over q squared. Okay, and so then this is the kind of thing that certainly contributes to your structured main term, so the remaining task is to analyze this off-diagonal contribution here. Let's see, can I just throw this up? I can. Neat. Okay, so then how are we going to analyze that? Well, here, if we're doing it in kind of this direct way, we would open the Kloosterman sum and apply Voronoi summation to each resulting sum over m and n, or in fact, just to one of them. So maybe I'll indicate very briefly what one could do here. So one could apply Voronoi in one variable, and then you pretty quickly actually come up with, by doing that, so it has the effect of converting these Kloosterman sums into Ramanujan sums that detect the condition that m and n be congruent to each other mod q. So that's another exercise to check that you can make sense of this, but I'll kind of fill in this exercise a bit on the next board. And then this we can analyze exactly as in 1. So it's kind of not something so new compared to what we've seen. So how would we see that most directly? So we'd say, okay, so if we call this, let's say 1 plus star, so star, let's think of now, maybe let's put the square root back in. I was hasty in taking it out. So then we have what? We have 1 over q, sum over a mod q star, opening the Kloosterman sum. And then we have a sum over m and n that we can factor as a product of two sums. So there's a sum over m of lambda m over square root of m, eq of ma, and then we have a sum over n of, let's say, lambda n bar divided by square root of n times maybe eq of n a inverse. I don't know, maybe I'll throw the bar all the way over there and negate the exponential. Okay. But now these sums we've already kind of seen in some form. So this is essentially f, sorry, I guess it's g now. So it's this modular form g that lambda is the coefficient of, evaluated at a plus I divided by q. Whereas this one is g conjugated, evaluated at negative a inverse plus I divided by q. With the usual caveat that we have to kind of remember the truncation of n to being of size q by this Whittaker function, so to make it precise, we got to use a different vector whose Whittaker function is that truncation. Okay, so in this optic, Voronoi is just the identity that g of negative a inverse plus I divided by q is actually equal to g of a plus I divided by q. And this is an easy exercise, actually. So all it amounts to observing is that these two elements are in the same orbit under SL2Z. So in fact, if we write, let's say, D for A inverse, so that we can make a matrix A, B, C, D, okay, maybe A, B, Q, D in SL2Z, and call that matrix gamma, then gamma will send one of these arguments to the other. So these two arguments are related via the matrix gamma. So the modularity of G gives that you have this identity, and this is just kind of a way to think modularly about Voronoi summation. So that's, again, a good exercise. If you've heard of Voronoi and you know what modularity is, check that this kind of modular identity recovers the case of Voronoi. So what that tells you is you just can replace this term here by the same term here. And so you're left with 1 over q, sum over a mod q star, and then magnitude of g squared evaluated at a plus I over q. If you remember, this last sum here was what we used to actually analyze this sum by the second of the two methods that we presented. Okay, and then we're in good shape, right? Because we can do, we can do the same analysis of that, for example, spectrally. I've kind of tacitly taken the central character of everything to be trivial here. So there's a new feature that shows up when that character is non-trivial, but you can basically treat it by the same reduction once you've formulated the argument in the way that is done here. So are there any questions on that so far? No, we're not relying on any factorization of Q. I don't know if that was your question, was it? That was your question? Okay, yeah. Yep. So I'll just kind of remark offhandedly as kind of an advertisement for maybe, interest in learning more about the theory of integral representations of L functions, is that, so there's this paper of Venkatesh, which is definitely listed in the exercises, that gives another way to view this kind of moment where you never need to touch the sums at all. So you use the fact that f times g 1/2, so it has an integral representation as an integral of f times g, and okay, I mean, what should this be over? It should be over something like upper half plane mod gamma naught of p. And then you want to take an Eisenstein series here. But, I mean, there's the issue of which Eisenstein series to take. And so it's kind of not the Eisenstein series for SL2Z, but maybe, I mean, you could think of it as an Eisenstein series attached to gamma naught p at kind of the big cusp. Or you could alternatively think of it as take the default Eisenstein series for SL2Z and then translate it by the diagonal matrix P1 on the right. And this turns out to give an integral representation for this L function by the theory of Rankin-Selberg integrals. So I'll just write that name here. So this is some integral representation of this thing, which then tells you by Parseval that the thing that we wrote down where on the top board, that I didn't give a name, so the sum over f that we're considering, L of f times g 1/2 squared, you can just understand as kind of an application of Parseval to compute the L2 norm of g times a of p e. But then this L2 norm we can alternatively think of as an inner product between the square of g and a of p applied to the square of e. So we turn it again to be in a situation where we can expand this spectrally and use the fact that a of p has decaying matrix coefficients off the constant function to get a kind of robust asymptotic formula for this thing, where the main term is kind of just the constant projections multiplied together of each of these things, and the error term is again robust and structured. So it's another example that would take some more time to kind of develop fully along the lines of this example involving discrete sets of points that we had over here earlier. Okay, and so with that, we got 4 minutes till we got to go. So maybe it's now a good time to stop and just to say in summary. So what did we do? We kind of outlined, as far as I can tell, the 4 convexity critical moments that we know how to use to prove subconvex bounds in rank 2 or bigger. We illustrated each of them in kind of the simplest possible case. And moreover, in each case, we indicated a couple different ways you can try to understand the method. So again, you can try to either understand it directly in terms of summation formulas, or you can dig around in the literature involving integral representations and try to use something like a Parseval type identity, like we did here, or like we did in the previous 2 examples, to obtain some other understanding. So yeah, thank you. Okay.